Okay, let's talk about rates of change. So suppose that we're talking about traveling somewhere, and we've documented the following. We have this table that we've been given time in hours, and then the distance that we traveled. So in 1 hour we've traveled 55 miles. Okay, so we could talk about this in terms of variables t for time and d for distance. We're asked to do something probably pretty simple that we understand just because most of us drive. We're asked to calculate the average speed or rate over a given interval. Well, let's talk about the formula. Distance is equal to rate times time. Okay, well here, let's go ahead and change this to D equals RT, right? Here we're asked to find the rate. And so if we're going to solve for the rate, we would have that the rate is found by taking distance over time. Okay, well I'm going to do this for starting off with the most basic interval here, which we could actually probably pretty easily understand, is I'm going to find out the average speed or the rate from when we start t equals 0 to 1 hour. And so just to introduce some notation, let's say that my rate, I would find it by finding d of 1, right? I'm using this function notation, the distance I've gone after 1 hour, minus the distance I went at 0 hours, and I would divide it by the time, and the time, it's just a difference again between 1 hour and 0 hours. Okay, so this is going to give us something that we could have easily understood, basically understanding what it means to travel in miles per hour, that sort of thing. So I look at this and it says the distance I've gone after 1 hour. So again, the distance here is going to be the dependent variable, depends on how long I've been traveling. Time, which is the independent variable. So d of 1 is going to be 55, and these are units, but I'm going to save that till the end. So 55 minus the distance I went after no time, which was I went nowhere, all over 1 minus 0. So I have miles over hours. And so I went 55 miles per hour. Okay, pretty basic for that starting example. But then let's start talking about what happens when I look at a different time interval, when I go from t equals 1 to t equals 2. And so let's just practice our notation, that rate, that speed I'm looking for. I can say I would take the difference in the distance traveled after 2 hours and the distance traveled after 1 hour, so d of 2 minus d of 1 all over 2 minus 1. So I traveled, it looks like from up here, I traveled 104 miles after 2 hours, where I started in this portion at t equals 1, I had gone 55 miles. And I would divide that by my units of time. So 2 minus 1 is going to give me 1 hour. So 104 minus 55 should be 49 miles. And so I would have for the second part that we traveled 49 miles per hour. Okay, so this probably makes a lot of sense. I'm just adding some function notation in there to get us started. But if you think about distance being a function of time depending on time, then we can start really thinking about this like d is like our y variable when we talk about Cartesian coordinate system, and t is like x. So I've got my independent and my dependent variable. And so what I'm really doing is I'm taking the change in the dependent variable and I'm dividing by the change in the independent variable. And so what we're seeing is we're actually I'll write it like this: change in distance over change in time, and that would be our change in our dependent variable over our change in independent variable. And if we think back to most functions, that's just our change in y over change in x, which we used to write it as like y2 minus y1 all over x2 minus x1. And then hopefully you're recognizing this as slope, where we denote that as m. Okay, so notice that we found an average rate of speed. We can say in general the average rate of change I'll put it down here. In general, average rate of change of a function f of x with respect to x as x changes from A to B is the following. We write it as f of B minus f of A all over B minus A. That is to say, a change in y values over the change in x values. Okay? Okay, and I pause it for a moment. Note this is the same thing as finding the slope of the line that passes through the points a comma f of a. So if I assign the x value as a, then the y value is denoted f of a. And then if I assign another x value as b, then the y value associated with that is f of b. So here we just have that this would be the same thing as the slope of the line passing through these 2 points that I've written here. Okay, so as soon as I see a question that says find the average rate of change, I'm going to start thinking about this difference quotient here, okay, the slope. Okay, so we're going to be asked to find the average rate of change. Okay, so here's a problem. Find the average rate of change for a function defined as f of x equals the square root of 3x minus 2, and we want to find that average rate of change between x equals 2 and x equals 6. And so immediately I start thinking about, as soon as I see average rate of change, I think about this difference quotient. I write down f of b minus f of a all over b minus a. And I remember that when I was looking at this earlier, it's like saying from 2 to 6. I'm going from where x is 2 to where x is 6. So I'm going to call this my a value and 6 my b value. And so as I go into interchange using this formula, I say, well, it's f of b, but I've said f of b is the same thing as now f of 6. And I'm going to subtract f of a. Well, I'm calling a 2, so f of 2. And then in the denominator, it says b minus a, so it's going to be 6 minus 2. Now what I need to do is realize this is just expressing function notation, and it's saying go back to your function, and everywhere there's an x, plug in the given value. So I'm going to come over here. F of 6 is the same thing as taking the square root of 3 times 6 minus 2. And then I'm going to subtract the square root. So I've got the square root of 3 times x, but x is being substituted by 2, minus 2, and it's all over 6 minus 2, which is 4. And so let's continue this out. So I'm going to have the square root of 18 minus 2, which is the square root of 16, minus the square root of 6 minus 2, which is 4. And so I'm going to have 4 minus 2 all over 4, and I'm going to end up with 1/2. So the average rate of change for this function between x equals 2 and x equals 6 is 1/2. Okay, well, let's put that back into context, because we were just working with a function. We didn't know what it was modeling, or if anything. But let's go back to the discussion about speed. And so this is just a plot that gives us the speed, and it gives us, I'm sorry, I should have said that it's giving us a plot of time versus the distance. And so this isn't quite linear, right? We have points that do not plot a straight line here. And so looking at this, though, I could determine, like, at different increments how far I've traveled. And so I could say, well, at 1.5 hours, how far did I go, and just read from the graph. But if I want to know the average speed, what I can do is essentially find the slope. That's what I'm doing. And if you notice, though, if I take, and I'm going to put some points over here, if I want to find the average speed between an interval, let's say like this, and then I want to find the average speed between this interval, and then maybe the average speed between this interval, and if I can change the color one more time, the average speed between these two little yellow dots, what I'm doing is I'm minimizing the time frame, right? I am taking at a half hour, I am looking closer and closer between, let's say, like a half hour and 37 minutes, 35 minutes. And so I'm shortening this distance here. And so what I'm actually doing is I'm determining what the instantaneous rate of change would be. So if I shorten this interval of time, I'm getting closer and closer to what's actually happening at the instant of 30 minutes, for example, on this graph. And let me just show you another image here, another table. Okay, so let's say I wanted to know what was going on at 10 seconds. Well, if I look at an interval from 10 seconds to 10.1 seconds, those are really close together. I'm determining an average speed using that formula. We're not using f of b, we're using s of b minus s of a, where this is a and this is b. But I'm determining the average speed at this really small interval, but I know that I could actually get closer and closer to 10 seconds, so I'm going to now look between the interval of 10 and 10.01, so I'm getting closer to 10 seconds, and so I find the average speed by doing my formula again, s of b minus s of a, where my starting point is 10 seconds, 10.01 is my ending time. And I can get even closer to 10 seconds, so perhaps I go from 10 seconds to 10.001. So anyway, the idea is that if I take the average speed over shorter and shorter intervals, I am getting closer and closer to the instantaneous rate of change, what the velocity or the speed is actually at 10 seconds. And this is the idea of limits. Okay, so let's talk in generalities here. Let's just say that we have another curve, and let's decide, let's using this A and B, let's just say that this point on this curve is the x value A. Let's arbitrarily call it A. And let's say that this point on this curve has the x value of B. Now, I'm not giving them anything other than arbitrary A and B, but I will tell you, perhaps, that this distance apart, let's arbitrarily call it h. And if I want to figure out how to denote the y value, you go, okay, with function notation, this y value is f of A, and this y value, well, I can call it f of B, but B is the same thing as A here moved over a distance of h, right? That's the same thing. I've moved over h. And so I can call this not just f of b, but I can call it f of a plus h. So these things are interchangeable as I've written them. Okay, so if I were to draw a line between these 2 points, I don't have a ruler here, so forgive that that should be a straight line, but this would be called a secant line. Now I can find the average rate of change between these 2 points, and in general I write down f of b minus f of a all over b minus a, and then I'm going to use the fact that I'm calling b a plus h. So this is the same thing as f of a plus h, just replacing the b with a plus h, minus f of a all over b minus a, but again I can replace b with a plus h, and then it says to subtract a. Okay? So and I can even simplify that further. So what I've actually got here is the average rate of change between these 2 points, and I can see that actually if this is called a secant line, what I have is that I've just defined the slope of that secant line, right? The change in y or the change in x. Okay, well we're talking about generalities, and I'm going to change some colors here. And let's say I am sticking with this point A, and I draw another point here. And let's just say now we'll call this distance away from each other h, this interval away. The space between, we'll call it h. I've now minimized the space. I can draw a new secant line. And again, I can find its slope using the same average rate of change definition. And if I think about minimizing even more so the distance apart, so I bring it, I hope you can see this little shadow, I bring these points closer and closer together. So I've minimized it almost just about as much as I can. If I draw this line, this is now called the tangent line. I have minimized h. H has gone to 0. That distance has gone to 0. What I have is I've taken and made h go to 0, or I write it in our terms, a limit as h goes to 0 of f of a plus h minus f of a, and notice those a's canceled out, all over h. So what I've done is I've minimized the distance, and I can actually see that I am now able to determine, by doing this, the instantaneous rate of change when x is equal to a. And this also gives me the slope of the tangent line when x is equal to a. Okay, now that's a lot to digest. Okay, so that was a lot to take in. So what we would call is this, this difference quotient, that is average rate of change. This would give us the slope of the secant line. It gives us average velocity. We would use this for the average rate of change in cost, revenue, or profit. And I've repeated this figure right here. And then we look to the right-hand side. That definition that I just gave you is instantaneous rate of change. That would give you instantaneous velocity. When you see the word marginal, talking about marginal cost, revenue, or profit, you would write this down. And this gives you the slope of the tangent line. And then the new term that comes up is this is also defined as the derivative. So our discussion about limits and how to find those becomes very important, because this word derivative is what we'll be dealing with for the rest of the semester. And so you just probably need to pause for a moment, take this in, rewrite it yourself, put it on a note card. But we've got on the left-hand side everything with average rate of change, that's the difference quotient here. And on the right-hand side, instantaneous rate of change, that's the derivative. And just as a reminder, when we're talking about profit, revenue, and cost, remember profit is equal to revenue minus cost. So that's something that you would have learned hopefully in the previous course. When we say the word derivative, remember you're going to think of all of these things, but you need to know that the notation is written as f prime of x. It's got this f prime of x. It's like an apostrophe here. Okay, so probably pause that, take that all in, but you can definitely see that there's a relationship, and that's developed from the idea of working with limits that we've been doing previously. Okay, so let's look at this next problem. So it'll ask you to find the instantaneous rate of change for a function at a given point. You will also note that it could have asked the same exact question in a different way. It could say, find f prime of x, or find the derivative of f, and f prime of 3. Okay, so these two things that I wrote here in green and red, those mean the exact same thing. So instantaneous rate of change means the same thing as finding the derivative. Okay, so what I'm first going to suggest is that you write down the definition. And so I would write down, as soon as I see the words instantaneous rate of change, or I see f prime, I'm going to say, well, I know what comes to mind is limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so good. We understood the definition. All right, the next thing I want to do is say, let's split this up. Let's first work with the numerator. And then we'll come back in and use our notation of the limit, and then we'll divide by h within there. Okay, so let's first work with f of x plus h minus f of x. Okay, so f of x plus h says everywhere in my function where there's an x, I'm going to replace it with the quantity the quantity x plus h. So f of x plus h would say x plus h all squared, because I'm replacing x with x plus h, minus 4 times the quantity x plus h, because I'm replacing x with x plus h. So this, written here in black, is f of x plus h. And then I'm going to subtract, like it says to actually subtract the function. Well, what was the function f of x? Let's change colors here. In blue, I'm going to subtract the function x squared minus 4x. And so just beware that you're subtracting a quantity. This is the function f of x. Okay? All right, so I'm going to be very careful. I'm going to make sure that I FOIL appropriately. If I FOIL x plus h, I'll have x squared plus 2xh plus h squared. I'm going to distribute negative 4x minus 4h, and then I'm going to distribute this negative sign. So I'm subtracting x squared and subtracting a negative 4x, which gives me a plus 4x. Okay, so remember, this is just the numerator. What we have done here is just the numerator. Now I have to simplify it, and it shouldn't be too terribly bad. So the x squareds cancel out, negative 4x and positive 4x. And so the numerator, I'll be taking the limit as h approaches 0 of so far this numerator. It's going to end up being 2xh plus h squared minus 4h. Okay, so this is just the numerator. So I'm going to make a note to myself. Now I'm going to divide by h. It says back over here, I'm going to divide that numerator by h. Okay, so I'm going to divide by h. Okay, look in the numerator. You have a common factor of h. I'm going to factor it out. And I see a nice cancellation. The h is in common. So I simplify, and I'm going to get 2x plus h minus 4. I'm now going to take the limit as h approaches 0 of that difference quotient that we have now simplified to 2x plus h minus 4. Well, it says h is going to 0, so I'm going to plug it in, and it looks like I have 2x minus 4. That would give me the instantaneous rate of change for any x. It's specifically going to ask me for x equals 3. This is the same thing as the derivative, so if it had asked in that way, I'd say that this is the same thing as f prime. But the question says, now find f prime of 3, or it says instantaneous rate of change at x equals 3. And so I know that that's the same thing. F prime of 3 means I'm going to go back to this derivative, or this instantaneous rate of change function that I found, and I'm going to say 2 times the x value it wants me to look for, which is 3, minus 4, and I would get negative 2. So this is the instantaneous rate of change for the function when x is equal to 3. Okay, so now suppose it goes further, and it says find the equation of the tangent line at x equals 1 for g of x equals 3 over x. Okay, so this kind of melds some things together. So I know that the derivative is the same thing as instantaneous rate of change, and I also know that that is the same thing as finding the slope of the tangent line at a particular point. Okay, so if it says I want to find an equation of a tangent line, that means that eventually I'm going to have like a linear equation, and I can start it off as y minus y1 equals m times x minus x1. Right, if I'm going to write an equation of a line, I need a point and a slope. Well, it's asking for equation of a tangent line, so this m is going to be the slope of the tangent line, which is found by taking the derivative or finding the instantaneous rate of change. It's given me the x value, so I've got the x value of 1, and all I have to do is find out what the y value is. So I need to find what the y value is simply by plugging in x to be 1. Okay, so the hardest part is going to be finding the slope of the tangent line. That just means taking the derivative, finding the instantaneous rate of change when x is equal to 1. And so the first thing I'm going to do is that simple part. I'm going to find g of 1. And so I have g of 1 is equal to 3 over 1, which is 3. So I have the point that this tangent line is going through is 1, 3. That's our point. And now I want to find the slope of the tangent line at that point, 1, 3. And I know that means that I'm going to have to take the derivative or find the instantaneous rate of change. And so I write down the limit as h goes to 0. This time we're talking about a function g, so it's g of x plus h minus g of x all over h. And here's where I need to make sure my skills are pretty sharp with that prerequisite material. Okay, so I'm first going to work with the numerator. Okay, g of x plus h. It says go to my function g, and where there's an x, plug in x plus h. Now it says to subtract g of x. Well, g of x is just the function 3 over x. Now I want to try to simplify, but the only way I can simplify is if I have a least common denominator. So my least common denominator will just be the product of x plus h times x. So I can't just arbitrarily multiply by x. I can multiply by 1, right? Something over itself is 1. So I'm going to multiply the numerator of this first part by x, the denominator by x. I've just creatively multiplied by 1. And then I'm going to subtract 3 over x, but I need to do it in a form where I've now creatively multiplied by 1. So if my LCD is x times x plus h, I'm missing a factor of x plus h. Can't just multiply it to the denominator, creatively multiplying by 1 here. And so if I simplify this, I will have the same denominator. That's what I wanted, a common denominator. I'll have 3x minus 3x minus 3h. And so if I simplify the numerator, I'll have negative 3h all over the quantity x times x plus h. Okay, if you look back at that that last example, second, we're going to divide by h. Okay. Now, if I said to you, and I'm going to erase this, take 100 and divide it by 4, you immediately go, oh, that's equal to 25. Like, you can give the answer. But if I say, let's rewrite it in a different way, let's pause for a moment and think about how that's also can be written. It can be written as 100 times the reciprocal of what I'm dividing by, or 100 times 1/4. Okay? So if I'm going to divide by h, I don't want to say I have a complex fraction. I mean, I can say I'm going to divide this whole thing by h, but that's goofy. Let's rewrite it so it's easier to work with as multiplying by its reciprocal, 1 over h. So now I'm going to divide by h. I've just done that by multiplying by 1 over h. And I can see that I can cancel the h's. And so in dividing by h, I now have negative 3 over the x times x plus h. And then my last step, just as we did a little bit ago, is to apply that limit as h goes to 0, minimizing that distance, that interval, so I can get instantaneous. So I've got negative 3 all over x times x plus h, but h is going to 0. And so I'm taking the limit as h goes to 0. I've got negative 3 over x squared plus 0 here, which means I get negative 3 over x squared. This will give me my instantaneous rate of change. For any x value, I just need to determine which one. They gave me one. This gives me my slope of my tangent line at any x value, but it specifically says that we want to know the slope of our tangent line when x is 1. So let me give myself some space here. So I'm going to denote this as f prime of x, which is the same thing as the slope of the tangent line, which is the instantaneous rate of change. And so for when x is 1, I have negative 3 over 1 squared, which is negative 3. And that is my slope of my tangent line. Okay? Now I go back to what it asked. It said to find the equation of the tangent line at x equals 1 for this function. Okay, so I've got a point, and now I've got the slope. Y minus y1 equals m times x minus x1. We're talking about a tangent line. We found the point. It said it was 1 comma 3, so y minus 3 equals the slope negative 3 times x minus x1. Our x value was given as 1. And then all I really have to do is finish this out rather nicely. Hopefully I didn't make any mistakes there. And now I've got an equation of my tangent line through the given point, 1 comma 3. Let's make sure I didn't make a bit. That looks like it's right.